Right, so in this example we're going to actually look at a WJC past paper question on differential equations. So again, the context is population growth, modelled by the differential equation dp dt equals kp. So they've skipped the proportionality part of the formula. They've already given you it as equals k times something, where p is the population, t is the time measured in days, and k is a causative constant. Given that the initial population is p naught, solve the differential equation giving p in terms of p naught, k and t. Okay, solving a differential equation, I only know one way. I have to separate the variables. So if I bring the p over, I get that. That's a straightforward natural log. And I need to put in an additional constant of integration. So be mindful here that there are two constants. I've got the constant that is in the original expression, the original differential equation, and then I've got the constant that's been introduced by integrating. Now, because I'm working with a population, p must be greater than 0. You can't have a negative number of people. So p must be greater than 0 as context is population, so cannot be negative. So I don't have to worry about that modulus sign. They want me to have a general solution with the constants in. So I'll take exponentials of both sides. And you'll see here, this is the third example now where this process of making that a different constant so e to the c is another constant, which is a e to the kt. So hopefully now that's the third example that we've had to do that, so you're getting comfortable with that step. Now if you look, they want me to have this in terms of p naught, k and t. Well, I got an a in there I need to deal with. It's telling me the initial population is p naught. I haven't got p naught in my formula. Initial means when time equals 0, population equals p naught. So p will be p naught equals a e, t is 0 to the 0. So e to the 0 is 1, so a is p naught. Hence p equals p naught e to the kt. So that is my part A solution to the differential equation giving p in terms of p naught, k and t. 4 marks. Part B, given also that k equals 2.5, find the time taken to the nearest minute for the population to reach 2 p naught. So basically for the population to double. So B, k equals 2.5 and p equals 2p naught. So p is going to be 2p naught equals p naught e to the 2.5 t. So I've taken my general solution. I know that the population is going to be twice what it started with, and that's going to enable the p naughts to cancel. And they're telling me that k is 2.5. So e to the 2.5t will be 2p naught over p naught. P naughts cancel. E to the 2.5t equals 2. I now need to bust into that exponential by doing the opposite, which is natural log. Leaves me 2.5t on that side equals ln t on that side. So t will be 1 over 2.5 ln 2. 1 over 2.5 ln 2 equals that. Does it ask us for any degree of accuracy? Find the time taken to the nearest minute, and t is in days, so that equals 0.277 days. So to turn that into the nearest minute, I need to times it by 24 hours and times 60 minutes. So times 24 times 60. So that equals 399.252 blah 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 blah. So that equals 399 minutes to the nearest minute. Okay, so that's part B. Part C. An improved model. In an improved model, the differential equation is given as dp dt equals lambda p cos lambda t, where p is the population, t is the time measured in days, and lambda is a positive constant. Given again that the initial population is p0 and that the time is measured in days. Solve the second differential equation. So we're repeating the process now, but we've got a different equation to solve. Separate the variables, and we have 1 over p dp equals lambda cos lambda t dt. 1 over p is natural log p. Again, we've established we don't need to put the modulus in, and I've already justified that in the previous part, so I'm not going to worry about justifying that again. When I integrate cos, I get sine. Because it's cos of a constant t, I divide by the differential of that, which is your reverse chain rule. So this side becomes lambda over lambda sine lambda t plus some constant. So the lambdas are going to cancel. ln p equals sine lambda t plus c. Take e. Do what we normally do now with that exponential. So that's going to be the same as sine lambda t times e to the c. P equals a e to the sine lambda t. So solve the second differential equation, giving p in terms of p naught, lambda and t. Well, we're not there yet. We know the initial population is p naught. So p naught equals a e to the 0 again, because sine of 0 is 0. So we're still going to have that constant being So general, oh my god, general solution will be P equals P naught E to the sine lambda T. That's your part C. Given also that lambda equals 2.5, find the time taken, given that also that lambda equals 2.5, find the time taken to the nearest minute for the population to double 2 pedo for the first time using the improved model. So same thing now, but with a different equation. When lambda equals 2.5 and P is 2P naught, so we've got 2P naught equals P naught E to the sine lambda is 2.5 T. So the P naught's going to cancel, and I'm going to get E to the sine 2.5 T equals 2. Then I'm going to take natural logs, and I have sine 2.5 T equals natural log of 2. To get into there now, I've got to do the opposite of sine. Which is sine to the minus 1. So T will be 1 over 2.5 arc sine of ln 2. Now, because we're working in calculus, you need to remember that your calculator needs to be in radians. Okay? Calc in radians. So here we go. Is mine in radians? It is, but if you can't remember how to do that, we're going to go to Shift, Setup, Option 2 for angle unit, Option 2 for radians. So I'm going to bang that in exactly as I see it. So fraction 1 over 2.5, Shift, Sine, ln 2, and then I close the bracket once for the natural log and a second time for the arc sine, equals that 0.3063, which I have to times by 24 and 60 to turn into minutes, times 24 times 60 equals, so 441 minutes. So the first model gave a time of nearly 400 minutes. This improved model is suggesting that it's going to take an additional 42 minutes for that population to double. So there you go. So that's a nice little past paper question there. How many marks is going there? So we've got 14 marks. So, you know, if you can get your head around these, integration tends to be nice. You're not testing really your integration skills so much, and they carry a lot of marks.